Thank you for being here, even if the clock is wrong, but it's time to start. So we are here for the PhD defense of Fernando Diaz. And Fernando, now you have the floor for some time between 45 minutes and an hour to tell us what you have done.
Okay. Thank you very much. Sorry. Thank you very much for the introduction. And well, as you can read, this is my defense about my thesis, which talks about the structure and dynamics of sign networks. So let me first introduce the object of study, which is sign networks, of course, that could be defined as the mathematical representation of antagonism within complex systems. By this, I mean that when we have a complex system, we usually need to account for its structure using a complex network. But when this system also has some type of antagonic interaction, for example, anticorrelation, inhibition, or conflict, we need to introduce some attribute in the edges, and this attribute is usually positive or negative, and thus the network becomes signed. And this type of antagonistic interactions appear in many different systems, from neuroscience, sociology, international relations, molecular biology, ecology, or even statistics and economics. So first, let me tell you about different research papers that have remarked the importance of these negative interactions in different contexts. In ecology, for example, negative interactions are essential to stabilize ecosystems. It has been shown that predator-prey interactions, which are positive in one direction and negative in the other, are stabilizing, whereas mutualistic and competitive interactions tend to be destabilizing. On molecular biology, on the other hand, the distribution of the edges, and in particular structural balance, which I will define later, are essential for creating irreversible networks, in particular gene regulatory networks. And several papers have shown that the gene regulatory networks of E. coli are arranged in a way that are flexible to external stimuli, so irreversible with respect to external stimuli, but robust with respect to internal stimuli. And this is thanks to the negative edges. In a financial context, it has been shown that this property of balance is correlated with high performance of traders in hedge funds. So when traders have work relationships that are balanced, they show increased returns when compared with unbalanced traders. Similarly, it has been shown that in teenager interaction networks, it can be predicted the type of interaction with an 86% accuracy by using the principle of triadic influence, which is very related to a structural balance. This means that relationships between teenagers are structured in a predictable manner. In neuroscience, it has been found that the brain shows two anticorrelated networks, two functional networks that activate or deactivate depending on whether the task is attention demanding or non-attention demanding. And finally, there is the seminal paper from the past century that proposed to understand international relations and power as a relational concept. This is that the power of a country is not only a function of its GDP or of its military power, but also a function of the positive and negative connections that it establishes with other states throughout the world. Based on all this, there has been a big effort to create a general and unified theory that is able to model all these systems with a unique set of tools, which is the theory of sign networks. And within this theory, we can differentiate at least four very active areas of research. The first is the empirical validation of structural balance, to take an empirical network and see whether it is balanced or not. The second is the adaptation of metrics to the sign context. So, for example, defining sign centralities, sign degree distributions, etc. Then we have the problem of network embedding, which is very important for data science and consists on embedding the network in a high dimensional space, respecting the structure imposed by the negative edges, and it's very related to the problem of faction detection. And finally, we have the problem of studying how the negative edges influence dynamical processes taking place on the network. Here we will talk a bit about all of these four topics. In particular, we will discuss structural balance in the context of international relations. We will talk about how to generalize communicability to sign networks. We will use communicability to create an embedding of the network in a high-dimensional Euclidean space. And we will also study the process of diffusion in networks. The talk is structured in 3 parts. First, I will talk about network structure, then about dynamics, and finally, I will apply the theoretical results in real data sets. Let me begin with the network structure part. And the first thing to do is to mathematically represent a network. Usually, the mathematical definition of a signed network is a collection of 3 objects: a set of vertices, a set of edges, and a function that assigns one sign to its edge. However, a more practical way of representing a signed network is through an adjacency matrix. This is a matrix that is square and whose elements are 0 if the corresponding nodes are not connected, 1 if they are connected through a positive edge, and -1 if they are connected through a negative edge. So for example, here nodes 1 and 2 are connected through a negative edge, so the element 1, 2 of the adjacency matrix is -1. There are many reasons why this representation is useful, but arguably the most important one is that it captures the walk structure of the network. As a reminder, a walk is a sequence of consecutive edges, not necessarily different, where these consecutive edges must be incident to the same node. So for example, 1 to 2 and 2 to 1 would be a walk because both edges are incident to node 2. The sign of the walk is the product of the signs of the edges. So that walk I just mentioned would be negative times negative. It would be a positive walk. And it turns out that the adjacency matrix, and in particular its powers, are able to count the number of walks of a given length k between any pair of nodes in the network. This is what I call the walk lemma. To see an example, imagine we want to enumerate all walks of length 3 between nodes 1 and 3. We could do this by hand, and for example, see that 1, 2, 2, 1, 1, 3 is a valid walk, 1, 3, 3, 4, 4, 3 is another, but you can see that this problem is very difficult when the network is even medium size. So we can alternatively take the third power of the adjacency matrix and look at the entry 1, 3. And here we see that there is a 5, which means that there are 5 walks between nodes 1 and 3, which are these 5. Moreover, you see that it is negative. That negative sign is indicating us that all of the 5 walks are negative. So basically, what this lemma does for us is to turn a hard combinatoric problem into an easy algebraic problem. And this is the key approach that we will use throughout the talk, turn combinatoric problems into algebraic ones. Now, arguably the most popular property of signed graphs is a structural balance, which was introduced by Fritz Heider in the psychological literature, but it was mathematically formalized by Harari in the 50s. This theory is based on the notion of balanced cycles. We say that a cycle is balanced when the product of its edges is positive, so when it contains an even number of negative edges. For example, balanced triangles are the ones that are intuitive to us, are either the enemy of the enemy is my friend, or the friend of the friend is my friend. They are intuitive relations. And whereas unbalanced triangles are the ones that are not intuitive. And we can generalize this to squares, to pentagons, etc. Then Harari defined a network to be balanced when every cycle within the network is balanced. Otherwise, it is unbalanced. For example, this graph only contains cycles with an even number of negative edges, so it is balanced. However, here we see that this graph contains one cycle with one negative edge, so it is unbalanced. The importance of balance is that it has a lot of mathematical consequence captured by the balance theorems. The first, which is Harari's theorem, tells us that when a graph is balanced, we can divide the node set into 2 balanced factions, such that all edges connecting nodes of the same balanced faction are positive, and all edges connecting nodes of different balanced factions are negative. As an example, if we take the network from before, we can rearrange the location of the nodes, and we see that there are two groups, and all edges within each group are positive, and the edges between the groups are negative. For the unbalanced graph, this is not possible because there is always one edge that violates one of these two norms. Another important consequence of balance is Acciaria's theorem that tells us that a graph is balanced if and only if the adjacency matrix of the signed graph and of the underlying unsigned graph, so the entry guy's absolute value, have the same spectrum, have the same eigenvalues. So basically, this is telling us that a balanced graph is equivalent to an unsigned graph from a spectral point of view. The problem with balance is that mathematically it's very well defined, but real networks never fulfill perfect balance because at some point there will always be at least one unbalanced cycle. So a very important problem from the methodological point of view is to determine how close a given network is to the perfectly balanced case. As an intuitive example, this network is unbalanced, but it only has this unbalanced cycle, but this network is also unbalanced, but it is clearly more unbalanced. There are many unbalanced cycles. There are four main ways of measuring this level of balance or degree of balance in the literature. The first one, the one that was proposed by Harari, is the motif-based approach, which basically counts unbalanced triangles, unbalanced squares as a proxy for the overall level of balance. Then we have the frustration-based approach that comes from the theory of spin glasses from statistical mechanics that finds the number of frustrated edges, that is, edges whose removal would balance the network. We have the dynamics-based approach, which uses a diffusive process and looks at the convergence towards the stationary state as a proxy for balance. And finally, the most popular one, I would say, and also the one that we will use in this thesis, is the walk-based approach, which uses walks as a proxy for cycles to quantify balance. What these four approaches have in common is that all of them evaluate the balance of the network as a whole. But it is equally important to know how much a given node is contributing to unbalancing the network. That is, we need also to know how to measure a local balance at the local level. As an example, imagine we want to know how much this node contributes to the unbalancing this network. Well, we could compute the cycles in which it participates, and we would see that there are two negative ones and two positive ones. So we would say it has medium balance. Now, how can we generalize this to arbitrary networks? First, we need a feasible way of counting cycles, but counting cycles in general is NP-hard. So our solution is to use the walk lemma that I said before and use closed walks as a proxy for these cycles. Second, we need to aggregate over cycles of different lengths. So what we would do is to include a weight factor, which I will always use the inverse factorial, such that longer walks don't overshadow shorter ones. That is the intuitive explanation. Now let's frame it mathematically. First, we have to count all positive walks and all negative walks of a given length, and the powers of the adjacency matrix already give us the difference. Since we want closed walks, we take the diagonal elements. Now, to take into account all lengths, we have to add up overall the indices k, but we have to include this inverse factorial penalization, and then this infinite sum converges to the exponential of the adjacent matrix, and in particular to the diagonal entries. Finally, we add a normalization constant that is related to the exponential of the unsigned adjacency matrix, and we find what we label the local balance index. We proposed this in this article. It is very similar to the global balance index that was proposed previously. The difference is that we are looking at the diagonal elements instead of aggregating them through the trace operator. So we have one balance index for every node. Now, we looked a lot at the mathematical properties of this index, and we found that it has several nice properties. First, it is bounded between 0 and 1. Values closer to 1 correspond to balanced nodes, and values closer to 0 correspond to unbalanced nodes. In fact, a network is balanced if and only if the local balance of every node is equal to 1. We also found that it can be interpreted as a measure of the loss of information due to the presence of negative edges. We found tighter bounds related to the degree. And we also found out that the global balance can be expressed as a weighted average of the local balance indices of the network. So up to now, we have used closed walks to quantify balance. Now, what we can do is to use open walks, and this would quantify effective alliances or entities. Again, let's look at the same example. And now we want to know whether nodes 3 and 4 are effective allies or effective enemies. If we look at the paths between the two nodes, we find that there is 1 positive one and 3 negative ones, so they are effective enemies, at least up to length 3. We will have the same challenges if we want to generalize this. In particular, we need to take all paths, so we will use open walks as a proxy for paths, and we need to aggregate different lengths, so we will use the factorial. Doing the same math as before, we would arrive at this matrix called the communicability matrix, which is the exponential of the adjacency matrix, but now we are taking into account the off-diagonal elements. And the properties of this matrix are, first, that it is positive definite. All of its eigenvalues are positive. Therefore, we can interpret it as the covariance matrix of a given random variable, sorry. That doesn't mean that the matrix is positive, though. It can have negative entries, and in fact, when the graph is balanced, a positive entry indicates us that the two nodes, that the corresponding nodes, belong to the same balanced faction. That means that the communicability matrix has within it the balanced faction structure of the network. It captures the balanced structure. Arguably, the most important property of this matrix, though, is that it can be used to define a distance. To understand better why this is important, let me review a bit the distance problem for a sign graph. We say that a function is a distance when it fulfills 4 properties. It is non-negative, it is equal to 0 if and only if the two entries are the same, it is symmetric, and it fulfills the triangle inequality. In network science, the typical distance that we use is the shortest path distance, or for weighted networks, the minimum weight distance. However, for sign graphs, we will run into a lot of problems, as I will show you now. Imagine we have this graph. Clearly, if we use the minimum weight distance, it is not positive, because these two nodes are connected via negative edge, so they will be at a negative distance. It is not 0 only when the two nodes are equal, because nodes 1 and 2 are connected through a path of weight 0, this path here, and it does not fulfill the triangle inequality. So it violates 3 out of the 4 axioms of a distance. Therefore, it is a really bad idea to use this in a practical setting. Alternatively, what we propose is to use this metric as a distance. Basically, what we are doing is we are aggregating diagonal and off-diagonal elements of the communicability matrix such that central nodes increase the distance and effective enemies, so entries that are negative, also increase the distance. And we proved that this is a distance, it fulfills all the axioms of a distance, and moreover, it is Euclidean. And this works whether the network is signed or unsigned, because the key property is that we need the matrix to be positive definite, and the communicability, as opposed to other matrices, is always positive definite for the factorial penalization. Moreover, I said that it is Euclidean. This means that this distance induces an embedding of the network into a high-dimensional Euclidean space. And when we have this high-dimensional embedding, we can define position vectors, we can define angles between nodes, etc. We can use the tools of geometry. In particular, the angle turns out to be given by this expression, and this object has very nice properties, even nicer than the communicability distance. First, it is also a distance. It is the angular distance on the hypersphere, but as opposed to the communicability distance, this is bounded. Moreover, we can interpret this as a correlation matrix, so we can use all of the properties and all of the algorithms that have been developed to extract information from correlation matrices. And it also captures the faction structure of the network, because angles between nodes belonging to the same balanced factions are always smaller than angles belonging to different balanced factions. So this concludes the first part about network structure, and the key messages that I want you to remember are: first, that walls are a proxy for both paths and cycles. Second, that we can leverage this to measure balance at the local and global level, as well as effective alliances and enmities. And third, that the communicability induces a well-defined distance, an embedding, and an angle between nodes. We will use a lot the communicability angle in the last part of the talk. The results are published in this article and this preprint. And now let me move to the second part, which concerns dynamics on sign networks. Now, the main dynamical process that we will study is diffusion. And as you know, diffusion relates the temporal evolution of a given field with its spatial inhomogeneities that are captured by the Laplacian operator. When we are in a network, the Laplacian cannot be a differential operator as usual. So instead, we use this matrix called the Laplacian matrix, which has diagonal entries equal to the node's degrees and off-diagonal elements equal to the negative of the adjacency matrix. This matrix is always singular, so it has always 0 as an eigenvalue. It is positive semi-definite. Its rows always add up to 0, and its null space contains always the vector of ones, the constant vector. Now the question is, how can we adapt all this for the signed case, preserving as many properties as we can? The solution is to include here an absolute value, to count the degree without looking at the edges of the nodes. And we could prove that with this definition, we obtain a positive semi-definite operator that is singular if and only if the graph is balanced. We lose the property that rows add up to 0, and its null space now, if the network is balanced, give us the information about the balanced factions in the network. The null space contains the information about the faction structure. Now, we can simulate or solve the diffusion equation with this signed Laplacian operator, and there is a powerful theorem by Altafini that tells us that there are only 3 possible stationary states of these dynamics that are determined by the structural properties. We can either have, if the network is unsigned, that all node states converge to the same value that Altafini called consensus, like in an analogy with opinion dynamics. We have that when the graph is balanced, the node states converge to 2 opposite opinions, or 2 opposite states, which is called dissensus. And this happens when the graph is balanced. And finally, when the graph is unbalanced, we have that all states go to 0, which Altafini called absence of opinions. This is quite remarkable because this happens depending on the structural balance of the network, even though when we defined the signed Laplacian, we did not impose any properties related to structural balance. So this is a clear example of this general principle in network science, which is that the network structure has a very strong effect on the dynamics taking place on it, and conversely, the dynamics can be used to extract information about the structure. Now, from now on, we will focus on the solution of the diffusion equation in a particular case, which is the one-dimensional chain. And for unsigned networks, it can be proved that the profile, the solution of this equation, is a Gaussian and therefore has 3 typical properties of Gaussian distributions. First, that the mean square displacement, the variance of the distribution, scales linearly with time. Second, that the full width at half maximum, that is the width of the distribution, scales with the square root of time. And third, that the maximum of the distribution decays with the square root of time. These are the typical scaling laws for a diffusive process, but there are many processes in nature which don't follow this scaling law. And then we call, when this happens, anomalous diffusion. In particular, when the mean square displacement scales with an exponent smaller than 1, we say we have subdiffusion. And when the mean square displacement scales with an exponent larger than 1, we say that it's super diffusive. And analogous scaling laws can be defined for the full width at half maximum and the maximum of the distribution. This is what will let us differentiate between the different diffusive regimes. But now we have to know how can we induce these different types of regimes that are observed in nature into our network. How can we model this? We will start with super diffusion, and the operator we will use is the so-called D-path Laplacian. This is almost the same as the typical Laplacian. The only difference is this thing here. Basically, this condition in the sum is telling us that the hypothetical particles that are jumping throughout the network cannot jump to the neighbors. Instead, they jump to nodes that are at a given distance d. Of course, if d equals to 1, those are the neighbors, and we recover the typical Laplacian. And in order to allow jumps of any arbitrary length in the network, that is long-range interactions or long-range jumps, what we do is to add up over all possible D-path Laplacian with a corresponding penalization factor. So the same idea as in the communicability. Now, however, the penalization factor is a power law with exponent S. So S controls the strength of the long-range jumps. And in particular, when S tends to infinity, this effective Laplacian, the so-called Megin transformed Laplacian, converges to the standard Laplacian. Now, if we include this new operator in the diffusion equation, what happens is that in the one-dimensional chain, and for values of S between 1 and 3, the system is super diffusive. And we can even characterize the exponent of the super diffusive scaling laws as a function of the parameter S. Okay, so we have super diffusion. Now let's model subdiffusion. To model subdiffusion, we use this operator called the Caputo fractional derivative, which admittedly it's a bit scary, but basically this is the way of modeling a derivative that it's not of integer order. It can be a derivative of order 1/3, for example. That order is given by the parameter alpha, and for alpha equal to 1, we have that we recover the usual derivative operator. The important thing here is that we have an integral over the usual derivative. This means that when we are evaluating this operator, we are not only looking at the local neighborhood of the node in time, we're also taking into account all the values of the node in the past, giving more weight to the present. So we are including a memory effect. This is a non-Markovian operator. Now, if we use this operator in the diffusion equation, the solution now it's a bit more complicated. It's not the exponential. Instead, it is a function that it's also a bit scary called the Mittag-Leffler function. And the key thing here is that because of this different solution, it can be proven that the time scaling now goes with this parameter alpha. So the system is subdiffusive as we wanted to model. Now we come to the main contribution that we did in this second part of the talk, which is to combine subdiffusion and superdiffusion in the same equation. And we called this the generalized diffusion equation. The subdiffusive part will be modeled by the Caputo derivative, and the superdiffusive part by the Megin transformed Laplacian. And we did this in this article from 2022. And well, solving this is not trivial. It takes a few pages, but it can be shown that now the time scaling depends both on the exponent alpha and on the exponent S. And the phase diagram shows that we can obtain the three regimes: superdiffusion, diffusion, and subdiffusion just by changing the values of the parameters alpha and S. With the same equation, we obtain the three possible regimes. We also ran some numerical simulations, and we found that the three different regimes appear in the same regions of the phase diagram. Now, very recently, there have been some approaches to try to include this generalized process and to exploit them to understand better sign networks. For example, we have this recent archive from summer that uses a non-conservative fractional diffusive process to motivate the use of a fractional balance index that uses these scary Mittag-Leffler functions that I mentioned before. And I also wanted to comment this, which is a work in progress that combines the results of the communicability and of the generalized diffusion. Basically, we use the communicability angle that I defined before, and in particular its cosine, to induce long-range interactions in a signed network. We are basically identifying the long-range interactions with the effective alliances and enmities in the network. By the way, here we use the communicability angle because the shortest path distance, as I said before, is ill-defined in a signed network, and therefore the results will be non-consistent. If we identify this matrix with the effective adjacency matrix and include a parameter S to control the strength of the long-range interactions, we can define again an effective Laplacian and look at the dynamics it induces. And the test network that we used is this one, which is unbalanced, but it has a very modular structure. And what we observed is that the parameter S has a very strong effect on the long-time dynamics. When S is large, so when we don't have long-range interactions, what happens is that we reach this dissensus in which all states converge to opposing states. This happens because of the very strong modular structure of the network, and importantly, this is not the real stationary state, because Altafini's theorem tells us that the stationary state must be absence of opinions, must be zero. What's happening is that the modular structure is creating a very long-lived metastable state that is deceiving us. In contrast, when we include the long-range interactions, so when we reduce the value of S, we reach the real stationary state. So the actually stationary state is recovered when including long-range interactions for reasonable times. Why does this happen? Well, basically, if we look at the adjacency matrix of the effective adjacency matrix, we see that there is some emergent imbalance. So for example, nodes 1, 5, and 7, which are not connected in the original network, are connected through a negative triangle, through an unbalanced triangle in the effective adjacency matrix because of these long-range interactions. So the long-range interactions are creating an effective imbalance that drives the system towards the correct stationary state. This concludes the second part about dynamics. The key messages are that, on the one hand, a structural balance is very important in dynamical processes in networks because it determines the long-time dynamics of diffusive processes. Secondly, that we can recover subdiffusion and superdiffusion with the same equation, with the generalized diffusion equation. And third, that long-range interactions can be included in signed networks, and they lead to new phenomena like this emergent imbalance that I mentioned. The results on the generalized diffusion equation are in this paper. The results about this are not published yet. Hopefully soon they will be. And finally, let me finish by exploring some applications of all the equations I discussed. Now, the good news is that there is no more math. Now the people who don't like math can join us again if you want. And the two applications that I will discuss are, first, the use of the local balance index to understand historical systems, and second, the use of the communicability angle to analyze data that comes from signed networks. We first will explore the historical part, and to better contextualize this, let me very briefly give an overview of the different theories in international relations. On the one hand, we have liberalism, which is a theory that states that democracy, interdependence, and institutions are able to promote peaceful relations among countries. And by the way, this article that I mentioned at the beginning is part of the liberalist most important works. And on the other hand, we have realism that says that international relations are anarchic, there is no higher authority, and therefore the only way of countries to ensure survival is to accumulate as much power as they can And this is the key reason behind conflicts. Now, realism has a evolution that is called structural realism that says that conflict is not the result of human nature, but a result of the structure of the international system. This is, in my opinion, the most appealing point of view from a complex systems perspective, because it, in essence, says that interdependence, that interactions and network structures are the key factors behind the presence or absence of conflict. Now, to understand a bit better this, we will explore the Russo-Japanese War, which is a war that happened in 1904 and pitted Russia and Japan against each other. This happened in the context of the imperialist age, so there were many different alliances and enmities interfering with this war. In particular, Russia was allied with France, Japan was allied with the United Kingdom, and Russia and the United Kingdom were strategic rivals because they were competing for control of Central Asia. Now, the key edge is this one, the positive edge between France and the United Kingdom, because, as I said, this happened in 1904, and that year also saw the signature of the Entente Cordiale. For the first time in centuries, in this year, United Kingdom and France stopped being enemies and became strategic allies. If you look at that, the signature of that agreement unbalances the network, and now if we would remove this link, the network would be balanced. And what happened in the war? Well, neither France joined Russia, neither the UK joined Japan. And it is quite likely that this link played a major role in preventing their involvement, because France joining Russia would have strained its relations with the UK, and the same happened if the UK joined Japan. So our hypothesis is then whether the topology, the structure of the international relations, influences or is correlated with the historical developments. And to test this, we developed a statistical procedure which compares data that we obtained from independent historical databases with, say, local balance time series that were extracted from alliances and enmities list extracted from the Correlates of War database. We compared how much the peaks and valleys in the time series matched with the historical events, and we looked at that with the real data and with randomized data in order to test for statistical significance, get p-values, and perform a statistical analysis. Let me give you a bit more information about how to extract the local balance time series. First, we took lists of alliances and enmities between the period 1816 and 2014 from this big project called the Correlates of War. And with this data, we created a temporal network, one network for each year that is signed. Then we computed the local balance of every country every year and built local balance time series, look like this. And finally, we looked at the peaks and valleys to see if they corresponded with historical events. To understand this better, let's look at an example. This is the local balance time series of Germany. And you see that there is a lot of ups and downs in the time series. And now let me show you what are the historical events behind them. The first peak corresponds to the revolution of 1848. These peaks and valleys correspond to the German unification wars. Then it is not marked, but this sharp drop corresponds to the dual alliance between Germany and Austria-Hungary. We have that small valley corresponding to the death of Kaiser William I. Oh, this valley that is also not marked corresponds to the Anglo-German naval race. That deeper valley corresponds to World War I, and the deeper valley corresponds to World War II and also to the onset of Nazi Germany, this small valley here. So we did this not only for Germany, but for every country, every year. And as I said, we tested if they match with the ground truth events that we found. And we did this first with the real data and then with a randomized time series. and obtained that the correlations in the real data were 10 times stronger and the p-value was essentially 0. So this is telling us that the information contained in the local balance time series, and in particular in its drops and increases, is statistically correlated, has some correlation with the onset of historical events taking place in that country in that year. Which type of events? Well, we saw that drops in balance correspond either to wars, to revolutions, or to violent conflicts in general, whereas increases correspond to peace treaties, to creation of supranational entities, or to peaceful independence from a colonial power. And why does this happen? Well, we believe that it has something to do with negative cliques. We proved mathematically that the existence of a negative clique drops balance exponentially fast, not only for the nodes participating in the negative clique, but also for the nodes that are close to the clique. The clique is so unbalanced that it leaks its unbalance outside of it. And we looked at the data and found that this clique appears in many important conflicts. For example, this big clique appears during World War II. We have a similar clique in the Middle East. We found this clique in Yugoslavia in the 90s. We found it in several African conflicts, etc. So we believe that this clique spontaneously emerges when there is a big conflict taking place. It drops the balance, and it's this balance drop that allows us to detect the conflict taking place. Now, let's explore how we can apply the communicability angle to analyze sign networks in a consistent way, and we will look at dimensionality reduction, faction detection, hierarchies of alliances, and inference of polarization. The dataset that I will use is this Gahuku Gamma dataset from tribes in the island of New Guinea. And this is a very interesting dataset, mainly because the hostilities and alliances are always the same. They reignite every year, every dry season, and are very stable over time. So it is a real anthropological system where we can test the mathematical theories. So the first thing that we would like to do is to visualize the network in a way that gives us information about the faction structure. We could use a typical layout, like the Kamada-Kawai layout, but we wouldn't be able to infer some faction structure from here. And this is because these layouts were not designed to handle negative edges. Instead, what we do is we use the communicability angle as a distance matrix and employ metric multidimensional scaling proposed by Kruskal that basically forces the network to be embedded in a low dimensional space, in this case, in a two-dimensional space in the plane, but tries to preserve the distances between nodes as faithfully as possible. And when we do that, this is the pattern that emerges. Now we see that there is a clear faction structure, one faction here and another opposing faction here, and we can even run hierarchical clustering in this low dimensional embedding to get a more fine-grained explanation of the hierarchy of alliances. For example, we see that this big faction actually corresponds also to two sub-factions that are hostile towards another if it were not for the Nagam tribe that acts as a bridge, and that is here in the dendrogram. So you may now raise the concern that I am using multidimensional scaling and hierarchical clustering, which are quite outdated and quite simple algorithms. But the good thing about this procedure is that we can use it with any dimensionality reduction algorithm or any clustering algorithm, because virtually every algorithm in data science uses either a distance matrix, a correlation matrix, or a similarity matrix as input. And we can get the three of them from the communicability angle. So for example, to cluster the network, we could use a spectral clustering, we could use DBSCAN, etc. For reducing the dimensionality, we could use t-SNE, UMAP, or we could even apply this for classification tasks. Now let's look at another example, which is the correlations between French representatives in the European Parliament in topics related to agriculture. between 2009 and 2013. If we group the representatives by their political group, we will not be able to see any structure appearing. That is because in the European Parliament, political affiliation doesn't seem to be a good predictor of voting patterns. Instead, what we did is to use the communicability embedding, and what we see is that there is a line, so the embedding seems to be one-dimensional, and the nodes spontaneously polarize when we go towards 2013, which, by the way, was the year in which the agrarian policy of the European Union was updated. So that is likely the cause of the polarized topics. And what we find is that in one faction, we find both the European People's Party and the Social Democrats, whereas in the other faction, we find all the new groups, the Greens, the Liberals, the far right. So the polarization is not on a typical left-right axis, but it's instead a polarization between the traditional parties and the emergent parties. Moreover, if we use the positioning of these nodes in the embedding, we can assign a level of polarization of every individual node. We can know how much a given representative is polarized based on their voting patterns. Finally, I will talk about an application of the communicability in international relations, and in particular looking at World War I. As you know, in World War I, the Entente, corresponding to Great Britain, France, Serbia, Russia, and others, pitted against the Central Powers that were Germany, Austria-Hungary, and the Ottoman Empire. All these countries declared war in 1914, but over the years, other countries joined the war effort. Those are the countries in light blue and in yellow color. If we use the communicability embedding with the network of 1914, what we see is that the countries that declared war in the Entente side are clustered in one pole and the Central Powers are clustered in another pole. More surprisingly, the countries that declared war later, so the countries whose war declaration is not included in the network of 1914, are also clustered together in the correct faction, except for China and Brazil. So even though we don't have still the information about 1915, we can predict with reasonable accuracy which faction they will join just based on the network of their alliances and conflicts. So we can classify and predict how the historical development of these countries. Of course, we can also run hierarchical clustering again, and we will see again ratified that the powers of the Entente get clustered in one branch of the dendrogram and the Central Powers get clustered in another branch. So this finishes the part about applications, and the key messages here are that local balance is correlated with historical events taking place in countries, that negative clicks seem to be the reason why this is happening, and that, on the other hand, the communicability angle can be used as a similarity, a correlation, or a distance matrix in order to perform data analysis over sign networks. The papers where you can find these results are the same I mentioned in the structure part. And now let me give you some general conclusions. I think probably the first conclusion that I want you to remember from this talk is that counting walks is a powerful tool, and it can be used as a proxy for cycles or paths in order to measure balance, to measure effective alliances. But also the walks have a very rich history in general in network science, and they can be also used to measure bipartivity, to define centrality measures, or even for community detection methods like InfoMap or Markov stability approach. A second conclusion is that balance is everywhere. We have seen that it plays a role in the dynamics, it plays a role in the detection of factions, and even is related to the occurrence of international events. But it is also important to recognize that balance isn't everything, and that there are additional mechanisms causing effects inside networks like status and homophily. Finally, I want to remark that sign networks are an important tool in data science, and this is because when we have data sets, it is quite typical to obtain correlation matrices from them, and correlation matrices are in essence an unfiltered version of a signed network. And mathematical results in this context are very important because they provide us with universal and general truths, admittedly in simplified settings, but that let us understand with certainty what is going on and to compare the real situations with these idealized settings. Finally, as future work, I think 4 main avenues of future work would be: first, to optimize the penalization that is included in the communicability and the local balance. I have used throughout this talk the inverse factorial, but there is no reason why in practical applications it has to be the best possible choice. So it is important to explore additional choices of this parameter. A second interesting area of future work is to explore more dynamical processes on signed networks. So first to understand these generalized diffusion models, and then to understand nonlinear dynamics in signed networks and what role negative edges plays there, or even dynamics of the signed network itself and how balance may emerge. Third, I think it is important to keep looking at what network science can say about international relations. And here, I think higher order, multi-layer, and temporal networks will play a key role because many of the features in international relations can be modeled as this. For example, alliances are a clear example of a higher order interaction. And in a more practical note, it would be nice to consolidate the framework I just explained by testing different clustering and dimensionality reduction algorithms to see which one works best, and also to explore how it works in classification tasks. So that is everything from my side. These are the references, the papers published in relation with this thesis, other papers that I published during the PhD. I thank you very much for your attention. And well, now it's time for questions.
Thank you very much. Yeah, certainly it's time for questions about being time. Do we need to use the microphone?
Yes. I think so.
No, I don't think so. Okay, so following the usual order in these cases,